Hi class, we are going to start 2.6 differentiability. I'm having a hard time pronouncing it. You can practice and help me. So this is the last section of the chapter 2. So we are going to study what differentiable, when we can take the derivative, when we can find the rate of change, all the same meanings. And we are going to actually do a lot of in-class activities in this section. So I want you to start with your in-class activities. Just look at this 1, 2, 3 graph and then try to find when the function is not continuous of this one and this one. And also look at the example we've seen before for limit. Also find when it's not continuous and when it's not differentiable. Okay, so pause the video and then think about it for 3 minutes. Okay, so did you get to find when it's not differentiable? Okay, so if you look at the first graph, I cannot, these are all actually continuous, right? This is all continuous. Since I cannot lift up my fingers when I was drawing, I can do one drawing. So when I look at this one, this A, actually, I cannot take a derivative because when I look at here's a corner, which means although it's a continuous, slope comes from here, slope comes from here, the slope value will be different. That's positive, that's negative. Therefore, we are saying that it's not differentiable. You cannot find this slope at A, okay, small a or that big A. Same reason. Now when you see here, I think they try to show that it goes like this and then bends like this. It's not polynomial as just a continuous. They just put as a piecewise. So that's what they want to indicate if you don't see it clearly. So that is also one of the part that if you take a rate of change, this rate of change, this rate of change, the limit is not going to be the same. So it is not going to be differentiable. And same reason in the corner. So does the limit exist at 0? Yes or no? Yes. Answer, yes, it goes to 0. I'm asking where the value goes to. It goes to 0. However, now I'm changing. My rate of change goes to 0, which means rate of change. F over a plus h, or x plus h this case, minus f over x over h. As h goes to infinity, 0, is that goes to some number. No, this one's a negative slope, that's a positive slope. So rate of change, which means I cannot take a derivative, or it's not differentiable at 0. So this one is undefined, or not differentiable. Okay, then let's look at next one. I want to compare the answer. That's what I got is -2, 0, and 6. There's an open hole. I don't think it's easy to see through this shiny screen. And then next one is disconnected. Here disconnected. And then when it's not differentiable, disconnected parts are these 3 numbers. And then y2 and 4. As you see, these are the also corners. So these are corners. So they are meeting like this way that the slope is different from each direction. So we are saying that it's not differentiable. So careful. So now in class activity 3, I want you to also pause the video and then graph carefully those 3. We also have seen this one, so as you think as a review, just try. And Youngha, I really have no idea. Don't forget, just a plug-in point. Try to plug in 2, 1, 0, -1, -2. Then you will see the shape, what it's gonna look like. So just trust me, plug in and get the graph and compare with me. So I plugged in point. And these are the points I plug in, and I hope that you got the same one. I just plug in 2, 1, 0, -1, -2. And then here I cannot plug in 0. So I left it as a whole. I cannot plug in 0, so I left it as a whole. Rest of them I just plugged in. So now I connected. Let's talk about this one. First, is this a continuous? Yes. Yes. How about this one? No. And this one? No. So I know that these two not gonna be differentiable, right? Then how about this one? Is it differentiable? This one? No, because it's a corner. Your slope is a negative this side, and then this side is positive. This one is going to be no, because not continuous. This is no. So I hope that you understand. Also remember the graph, okay? We've seen this one. So welcome to main dish. I tried to go a little bit faster this part because before I took so long of a 1 hour lecture. So main dish. Again, we are going to continue talk about the when it's not differentiable. and discuss when the function is not differentiable. So this is a function, and then as you say, x to the 1/3 power. When you look at actually this function, I know that it is continuous. Then I want to see, here's a function not continuous, differentiable at x is 0. It's not differentiable here because there's a vertical tangent. How do I know? Because for me it doesn't look like a vertical tangent because we didn't know that before when we were taking pre-calc. So I'm going to take a derivative. Then, do you remember 1/3 comes to the front, and then take -1, which is 3/3. So that will give me -2/3. I took the derivative. I'm going to organize this one. Then you see that 1/3 square root of x cubed. You can pull x squared out, that's fine too. But when I look at my derivative function, there's my 0 there. You see it's undefined, right? So that's what they're talking about. You see that already when I try to make this one equal to 0, already denominator is undefined as 0. So therefore, slope doesn't exist as 0. What does that mean? Slope is not exist, but it's continuous. That means only way you can have that slope should be vertical slope, right? So, because I know that this is a power function, that's how you can deduce here. So we didn't learn about the vertical slope the whole time until calculus. Now you know the calculus that you can prove it. When you take a 0, also another way you can just take equation here, and that's going to be 0 is equal to 1. That doesn't make sense. So it also shows that mathematically x do not exist as a 0 at all. Okay, next one. Now, do you see the piecewise function? It connected those two. Basically, that's what happens if you are in tier 1, then you pay this much. If you are in tier 2, you pay that much. So that's kind of a lot of bill plans, and the electric PG&E plans has this kind of a graph. So when I look at this, we've been talking about it. The slope here is going to be different. That this is not differentiable. However, it is continuous. So now let's look at, as a main dish, one of the algebraic continuous, considering when the function will be continuous. So let's see if we can graph this one. 2x minus 3. So y-intercept minus 3, slope is going to be 2, and then they say x is less than 0. So I have to actually graph it below here. So I have this graph, just look at it, but my x is going to be only less than 0. So this is going to be 0, so less than 0, and then closed circle. Next, I'm going to graph x squared minus 3, and x is greater than 0. So do I know x squared minus 3 graphs? Yes, I know x squared graph, and then move down 3. So I'm going to have this coordinate. Let me see. So this one is an open circle, because if it's a closed circle, it's not going to be function, right? Because two outputs, and then if you plug in, you are going to pass through those points. I pass through 1, comma, -2, and this one's a 2, comma, 1 by plugging numbers 1 and 2. So I get my graph this way. Then now, is the function g continuous at 1? At 1 here, continuous, yes. Is it differentiable at 1? Yes, because it's continuous. Also, you see there's a smooth function, right? Smooth function, not those corner function. Is this continuous at 0? And 0 is right here. Is this continuous? Yes, it is continuous. Then, is this differentiable at 0? No, it's not differentiable. Okay, I hope that you're understanding. I repeat it a lot, right? So there's an appetizer. I want to graph and answer, and then compare with me. Okay, let's compare the answer with in-class activities. First, I graph x plus 2, that's orange color, starting from 2, and then slope 1. But they said that I can only have less than 1. So here's 1, so I'm going to delete this part. And then I graph 4x minus 1, you can plug in numbers, or -1 as y-intercept, slope 1, 2, 3, 4 over 1. So it starts from here, and this green color is a graph, but they say that I'm going to use that graph from 1 with open circle. So this is my graph. Continuous at 1, continuous at 1, yes. Differentiable at 1, no. continuous at 2, right here, right? Continuous at 2, yes. Differentiable, yes, because it's a continuous one function. Slope is the same also, left and right. Okay, so let's continue dessert, and then I want you to get also Desmos ready. Okay, we are on dessert. It's going okay, right? So when you look at this one, scary, right? So we are going to apply some real life questions also using Desmos.com. I want you to get used to, and then also make sure you read questions very carefully when you do the homework so that you don't get frustrated. But also the function, when I looked at it, you can actually do it without graphing calculator. So I will show you also how I can approach without graphing calculator. Some of them you cannot actually use it with graphing calculator, like this example, not gonna graph it with a graphing calculator. Why? Because we don't know the value. You cannot even punch in. So let's look at our dessert number 1. Also, it will be in class activities 5. Just do together with me. So zooming on the graphing calculator, we're calculating the derivative from this one, definition of derivative. Okay, so I'm going to use what the function will look like. Do you see that? I can see two cases. If x is greater than 0, then my function is gonna come out as x plus x minus 1, which is 2x minus 1. Because the absolute value number will be always a positive, so just come out itself. X is less than 0, or you can put actually equal to. Then it's gonna be x minus x. Because if you plug in -4, you wanna make it +4. So you have to give them negative outside. So I give the negative outside, so negative x, and then -1, that gives me -1. So do we know that graph? We practice even harder one. So that's why I'm saying don't be afraid. So that's a 2x minus 1. I'm going to graph here when x is greater than 0 or equal to. So close circle and 2x. Then I'm going to graph when x is less than 0. That's going to be -1. See, I told you it's not too bad, right? So I graph this one. Now, is this function, can we find the derivative at 0? Can we find the derivative at 0? No. By graph we proved it. Then they say definition of a derivative, use the definition of a derivative. Oh, what do I have to do? I have to do that limit of f over, this time a plus h minus f of a over h. Okay, so I will do top part, you do bottom one, okay? So I'm going to plug in 2a plus h minus 1 minus 2a minus 1 over h, and what I get is 2a plus 2h minus 1 minus 2a minus 1 over h. A lot of them cancel out. Oh, that's plus, right? Cancel out. So I get 2h over h. I use the definition. Cancel out. I get 2. What does that mean? Positive side, I noticed that the slope is 2. I'm going to use now fancy notation. df dx is 2. What does that mean? That means a slope in derivatives. Derivative slope, right? So it's going to be changes in y over changes in x. When you take the limit, that's what you get. Okay. I want you to know all the notation because we use this one later a lot and it will be very handy to know. Now, I want you to try taking derivative using this one definition. Can we even use definition? No, it didn't seem like we can plug in anything, right? So from here, what I can do, I can just look at, and then -1, if I take a derivative, although you plug in, I don't even know how you can plug it. So -1 minus -1 over h equals 0. I think your slope is going to be, oh yeah, -1, it's going to be -1 plus 1 over h, and then that's going to be 0, that's going to be 0. Oh, never mind. There's something, I made a little mistake somewhere. So that is going to be slope 0. So as you see that, also limit not existing by showing the definition. So I also wanted to show you can punch into the Desmos. So look at here, I punch into Desmos, and then I use the absolute value as your keyboard shows those one bar right above this kind of notation. So check and find that. So if I look at this one as I desire, also we graph in the classroom together, it shows exactly same graph. So you can also check your answer with the decimals, and that'll be really useful. So let's look at this one, number 2. It looks scary, right? So just listen and then follow here, then you will see actually it's not too bad. So here says the acceleration of due to gravity g varies with height above this surface of the earth in a certain way. If you go down below the surface of the earth, gravity varies in a different way. It can be shown as g function shown below. Okay, so let's look at what is going on. I have earth here, and they said big R is the radius of earth. Is this fixed? Yes, right? And the mass of the earth, is that the number or variable? So number, already is a number is a fixed too. So it's going to be number, and then g as a gravity constant. I think that's a 9.8 something, right? Negative or positive. And that's going to be also fixed. So all the g, m, r are all numbers. Then small r is the distance to the center of the earth. So you can be r as here, it can be r as here, it can be r as here. What they're saying is your radius is location is bigger than r. If your r is here, then you're gonna use first one as your function. If your r is function, I need to change one of them, right? Let me double check. It's gonna be okay. Fix this one. It's going to be less. Yeah, now it makes sense. If r is less than r, big R, then you are going to use first one. So you are going to use below, under the earth, you're using this one. And then if it is r is bigger, you are located outside of the earth's surface, then you are going to use this one as gravity. Now look at here, in place r, output is gravity. If you look at this function, what kind of function does this look like? Do you see that this is a number times r? What function is it? This is linear, right? So it's going to be a linear function. What about next one? Number over r squared. Do you see as a 1 over x squared function? It's going to be rational function. And it's going to be linearly this one increasing like this. That's going to be rational function this way. But since it's going to be gravity, radius is going to be always positive, that's going to be this part. So now they are continuous? I don't know. How do I know that it's continuous? I need to check that when r value, when it's the same, when it meets right here, it has to be connect as the same value, right? So let's plug in small r. What happens? If I plug in small r, this becomes gm and over little r cubed and r, because I can plug in this r into big R. If you simplify, that becomes gm over r squared. Second equation, if I look at it, it's already exactly the same. That means they are connected. They are connected at r. So let's graph it. Before, when r is less than big R, it's going to be starting from 0, 0, because you don't have y-intercept, and it's going to be increasing. What happened? It's going to be when r and r is the same, then the graph is going to be look like 1 over x squared function. So that's my graph shape of the given function. Looks hard, right? But you got it. If you follow, that's totally good. And now we finish the graph. Is g continuous at r? G continuous at r? Yes. Is the g differentiable at r? No. Okay. You will see some of this question, actually 3, 4 of them on your homework. So make sure that there's one more. Do it and then compare with me. Keep think about what is the input. There's a blank, and then try to see what kind of graph it's gonna end it up with, and then roughly graph it by yourself. Okay, I'll come back.
Did you understand the equation, class? When you look at this one, did you find what is the input?
Actually, the input is a t, so that's the input resonance is a constant. So what this function is about electric charge. Q in a circuit is given as a function with time t. So whenever you time has, and then what is the electric charge amount is given by function. So you can actually think about this way. Your constant or those plugs, I don't see any around me right now. And if you have those plugs, when you plug it before on the wall, you have those plugs, right? But do you know that actually there is a current there? There's electric charge still going on. There's a little bit of it. It's not always a zero. And then when you plug it, it's gonna actually shoot it, and then it's gonna actually use it there. So if you look at this one, first when you look at function, when I plug in 0, I got C, and the second one also I plug in 0, then that actually gave me C. So I know that at 0, it is continuous. It's connected, right? They're at least connected. And can we graph this one? Let's graph this one together. So first C, you just choose. C can be 5, C can be 3. So I will just choose as a 3. So C, when time goes by, it's going to be like that. And then as soon as t is going to be 0, oh, that's before time is starting. So I'm going to draw here because that's going to be t. So it's keep running. And then electric charge is going to be transformed the other side. So it's going to have the function. But when you look at this one, do you see my function? I don't see it, right? So you have to be careful looking at this function. It's gonna look like e to the negative. Young, how do you know? Because I know that big picture, c times e to the negative 1 over rc, and then to the t. If you look at it, this is a constant, this is a constant, this is a constant. So the big picture is going to look like e to the negative x function, which is e to the x is this way, the e to the negative x will be flip it over y-axis. So now my function is going to go this way, and then we prove that as c, this is going to have the same y value, so it is continuous. So I graphed it. Is the charge continuous of the function at time t? Yes. And do you think the current is defined for all the time? What does that mean? Current I. So what are they asking? Here says some weird concept here. What is a current? We say current is actually electric charge over time. That's what current is. So that's why this much per time is gonna how much your electric charge is gonna transfer. That is what we call as a current. That means they just put it hard way, but basically, do you think the rate of change is defined at all the time? That's what they're asking. Because the current is, they said that's a derivative of this function over time. Then what will be the answer? Is it defined all the time? Is it defined all the time? Is it differentiable all the time? No. So, no, it's not defined at 1. That means your current is not defined at time is 1. Okay, so that's the answer. And good job. I hope that this one was helpful, and then this went by a little bit faster, right? So when you do homework, you will have these questions, keep related, and then don't feel scared about it. Just look at the big picture of what function they're talking about after you found the constant values. And also you can use decimals, but this one's not going to be, but there will be a couple of questions. Homework says use the graph or zoom the graph. You can use it, but also I checked it, you can graph it like a me. Just looking at plugging some numbers, and then make sure you read question carefully. Okay, so that was all about chapter 2.